Hello, Francesco. I'm you. Hello, Francesco.
I can't do that. I don't have
you.
No, I don't have account in Facebook.
Hello, Francesco.
I can't do that. I don't have
you.
No, I don't have account in Facebook.
Hello, Francesco.
I can't do that.
you.
Ti si ipak tu, Ljubice.
Pa ja sam
No,
tu.
I don't have account in
Mi smo
Facebook.
samo
Hello,
preželjeli.
Francesco.
I can't do that.
you.
Ti si ipak tu,
Popravio mi
Ljubice.
se internet. Pa ja sam
No,
tu.
I don't have account in
Mi smo
Facebook.
samo
Hello,
preželjeli.
Francesco.
I can't do that.
you.
Ti si ipak tu,
Popravio mi
Ljubice.
se internet. Pa ja sam
No,
tu.
I don't have account in
Mi
Facebook.
smo samo
It was a bit chaotic. Yes? Measurement. Ok. Vidio sam. Ok, ajde, samo ti dođi i uživi. Ćao. Okay, let me. SIS website, you said, yeah? Okay, let's try. SIS. It doesn't go that way. European, not Union, that is European Structural.
links about us activity.
Finally, I am a bit.
Live.
Okay, finally. So, where do we look now? Publications and video. Live, YouTube channel live. Okay, live. Live, yes. Okay, I see it. Great. Live, yes. Okay, I see it. Great. I did. I did. Okay. This is multiplication of reality. I did. This is multiplication of reality. I did. So why do we still have this noise?
Mikrofonija.
Which one? I have closed everything. Which one? I have closed everything. But I still hear myself. Oh my god. Oh, now what? I have closed everything. But I still hear myself. Oh my god. I can hear it, but I cannot see it. Okay, I'll handle that somehow. Even if I reset the computer.
Francesco?
No, Leslie.
Hi. You can hear me. Hi.
Yes.
What is that noise? I still hear it. I still hear it, Francesco. Do you hear it? Hi, Jim. You're muted. You're muted, Jim. You have to unmute. You have to go to the bottom and
Okay, I just
unmute.
turned on microphone.
You
Did
did
that
it.
help?
That's great. Now we can hear you.
Good, good.
How are you there in Massachusetts?
Oh, hunkered down.
Okay,
Yeah.
Francesca, if I must, can I just say a word? Francesco, can I just try to share my screen and look that my presentation works?
Right.
Okay. Present now, yes? Your entire screen. And I click and I share. And here it is. Wait, let me
Okay.
just. Perfect. Okay. So now I'm going to stop sharing.
Okay, and your topic takes me back to my undergraduate thesis.
That's where I'm going to take you.
Okay.
My husband didn't particularly think that my title was very good. It's interface fracture a la rice.
Oh my.
Anyway,
Yeah.
happy birthday. Happy
Thank you.
birthday.
Thank you. There's no way to suppress them. They keep happening.
That's the best way.
Yeah.
How is Renata?
Oh, her health could be a lot better, but she's
Hanging in there.
hanging in, sort of. Yes.
We'll send her my warmest greetings, okay?
Okay, will do.
Francesco, I Jim, you're silenced. Jim, you're silent. You're muted.
Yes.
At the bottom of your screen, Jim, again, if you raise that bottom part of your screen, there's a microphone, and you've got it off. That's your problem.
Okay.
Now you have it on.
Okay. This
That's
works.
That's the on and off. Okay.
And do you hear me now?
Yes. Yes, I do.
Oh,
yes.
good. Okay, thank you.
Okay. Alexander, are you going to start?
No, Francesco.
Ah.
Ružice, mute it. Thank you, Francesco. So it is my turn to say a few words. Today, we are actually following this 2020 annual conference of Serbian Society, and we decided to dedicate this conference to Professor James Rice on the occasion of his 80th birthday, and it happens to be today. So we are gathered here to honor the man who has established scientific base for elastic plastic fracture mechanics, introducing thereby J-integral and HRR fields, just to mention that, and then also just a few other contributions like fundamentals of fatigue, fundamental equation for micromechanical modeling, and all these three in late 60s, whereas in early 70s, we have significant contribution in computational fracture mechanics. That was with linear elastic plastic, and some other aspects of crack tip elements, finite elements. I dare say that even nowadays we have improved a lot. We have made many advances, but I dare say we are still recycling these gigantic results from late 60s and early 70s. So it is therefore my privilege, really big privilege and honor, to congratulate Jim on his 80th birthday on this occasion, and to say long live Jim, and cheers.
You're very kind. Thank you.
So naturally, it's your turn now.
Well, what can I say? I'm just deeply honored to be invited to this occasion, and I fondly remember the visit there for the last session. I met many interesting people, and I'm happy to see some of the faces again now. And I guess in my own research, we still focus on fracture, but it's mostly in the context of nucleating ruptures in rock materials and their propagation in earthquakes. So we've been in my small group trying to carry the ideas of fracture mechanics into seismology. And I must say, we've gotten a lot of help on that from the seismological community. People within that have picked up these ideas, not necessarily via me, but via just looking at what's going on out there in the fracture literature. And nowadays, when you read papers and proceedings on earthquake phenomena, you just see concepts of fracture mechanics rather routinely brought in. So for me, it's been nice over recent years to see this merger between the kinds of fracture mechanics that Paul Paris, the late, sadly, Paul Paris, introduced me to many, many years ago, and what's currently happening in adjacent fields.
Thank you, Jim. So just to make a small conclusion before Leslie takes over. Contrary to nowadays very popular nanomechanics, including nanofracture mechanics, you are actually involved in a kind of macro and global fracture mechanics.
Right. Right.
Okay. So this was, I would say, introductory part. Once again, it's really greatest pleasure to see, not only to talk about, but to see Professor Rice in person, almost. And now, Leslie, please
if I
start
could add
with your talk.
there.
Yes,
Yeah,
of
if
course.
I could add something, it's
Yes.
a great delight for me too to see my friends, newly made friends as of the conference last time in Serbia, but also it's such a pleasure to see former co-workers and students here. For example, Leslie Banks Sills visited as a postdoc when I was at Brown, right? Yes.
Right, right.
That was at Brown, and then I've had outstanding students at Brown and at Harvard, and two of those outstanding people you can see at the top here, Rizica and Sinisa. So Serbia has kept me well supplied with good students in that era.
That's nice.
Thank you. Thank you. Leslie, please. Leslie, please.
Okay, well, it's a pleasure to be here. And I'm so happy to be able to honor you, Jim, by giving this talk. Alexander turned to me a few weeks ago and asked me if I would write a paper with him and on interface fracture. So he and I have written a paper together. We took different directions. I hear myself in an echo, Francesco. Do you? I don't know why. Well, anyway, I hope it'll go okay. So we wrote a paper together. I took it to mean a historical perspective, and as you'll see, Alexander looked more at his work as it was influenced by you, Jim. So I'm going to speak historically now. So I'm going to try to put up my screen. Francesco has taught me how to do that. And here it's going on. Okay, but I don't see it. Wait, okay, and now you all can see it. I just want to bring in a pointer. Okay, so I have very much been influenced by the work of Jim Rice with my group, and we've been using tools of interface fracture mechanics for many years. So although my husband didn't like my title, a la Rice, but I think it's a great title, Interface Fracture a la Rice. And I'm going to give you a historical perspective of interface fracture. And in particular, I'm going to spend a lot of time on slides that are related to papers that, in particular, the 1988 paper that Jim wrote. So I will start by talking about linear elastic fracture mechanics, and then the early years of interface fracture mechanics, and then the contribution of Maria Komnenau from 1977 to 1979. You'll see why I'm looking at that. And then I will spend a lot of time on Rice's paper from 1988, because that paper really lays the foundation of how we look at interface fracture mechanics today. So I start with the paper by Griffith from 1921, and I think of Griffith as the grandfather of fracture mechanics. And he showed that the stresses at the tip of a crack in a brittle material behave as the inverse square root of the crack length. And he also presented an energy criterion, which we use today, the Griffith criterion. And then the next major step in understanding fracture takes place when the first term of the asymptotic expansion for the stress and displacements in the neighborhood of a crack tip is developed by Williams and Irwin. And I'm talking about a crack in a linear elastic, homogeneous and isotropic material. And Irwin, who I denote as the father of fracture mechanics, defined stress intensity factors K1, K2, and K3. Then we come to interface fracture mechanics, and really right on the heels of what Williams does I can't see on my screen, but at the bottom of my screen, I have Williams' paper from 1959. So in 1959, Williams derives the behavior of the stress and displacements in the neighborhood of a crack tip for a crack along an interface between two dissimilar linear elastic, isotropic, and homogeneous materials. And what he finds, and if we look at the little drawing here, we have material 1 above the X1 axis and material 2 below the X1 axis. The X1 axis is the interface. And he finds that the stresses behave as 1 over the square root of R, which is just fine and dandy. But then he has the sine epsilon log R and cosine epsilon log R. Epsilon is related to the mechanical properties, and it's small. We'll look and see how small it is later. But we have this log R. So as R goes to 0, the log goes to minus infinity, and the stresses within this square root singularity are oscillating ever so fast as we approach the crack tip. And the displacements, which weren't looked at so completely, what it does predict is that in the neighborhood of the crack tip, we have crack face interpenetration, which is physically untenable. So, but be that as it may, Williams, this was a very important paper, explained to us how the stresses and displacements behaved. And this quantity epsilon, known as the oscillatory parameter, is related to the mechanical properties, as I said, of the materials, where mu k are the shear moduli. K equals 1 is the upper material, k equals 2 is the lower material. And kappa, this Mushkulashvili constant, whether we have plane stress or plane strain, and nu k are the Poisson's ratio of the upper and lower materials. So we have to keep our eye on epsilon. So then between 1963, we recall that Williams' papers from 1959, we have a whole bunch of papers which solve specific problems, specific geometry, and specific loading. And the first term of the asymptotic expansion for the stresses was determined. And it was noted that the oscillatory behavior was relegated to a small region near the crack tip. And this is what was said. Whether that's true or not, we'll discuss it as we go. So then in paper number 8, which was really a very, very important paper, and this is a paper by Jim Rice and George Seif when Jim was at Lehigh University, they find the stress intensity factor for the problem of an infinite body composed of 2 materials with an interface with a crack of finite length 2a along the interface, loaded at infinity by sigma 2,2 and sigma 2,1. And then I'll say something about sigma 1,1 and sigma 1,1,1 for the upper material and sigma 1,1,2 for the lower material. So they found K. Now their K was in a bit of a different form. I put it in today's form. In the paper, I actually give the other form, but I think it's easier if we just look in today's notation, current notation. So K, we have a complex stress intensity factor where K1 and K2 are real. I is the square root of -1. And it's related to the applied stresses, the tensile stress and the shear stress, the oscillatory parameter, and the crack length. And or maybe I should just say one thing here. Suppose we took sigma 2,1 infinity was equal to 0. You can still see that you're going to have a K2 component. When you have isotropic homogeneous material and you put sigma 2,1 equal to 0, there's no K2. But because of the form of the solution, there is a small K2 when sigma 2,1 is equal to 0. And another very important part of that paper, number 8, was in the appendix of that. It's in the appendix of that paper, telling us that we should apply sigma 111 and sigma 112 in order to get displacement continuity along the interface far from the crack. So this was really important, and I spent a long time not doing it correctly and getting finite element results which were not correct until I discovered, you go back and when things aren't working and you just reread the papers and you find out what you did wrong. So I found out what I was doing wrong. And just to tell you that E bar is sort of a generalized Young's modulus, where it's EK over 1 minus nu K squared for plane strain and for generalized plane stress. Generalized plane stress, sorry, there's an error there. It should be generalized plane stress. It's EK. And it was noted in that paper that these stress intensity factors no longer represents mode 1 and mode 2 deformation, and the in-plane deformation is coupled. As I explained when I first started talking about this slide, I take sigma 210 and I still get K2. So now there's a paper number 9 by England, and it's from 1965, and it was found, again, the stress oscillations are confined to a small distance from the crack tip. That's what's said in the paper. And in fact, it was also found that cracked face interpenetration was also within a small distance from the crack tip, and in particular, the region was estimated to be 10 to the minus 4 times 2A. And it was noted that this is sufficiently small so that it may be neglected, and thus the solution to these problems may be a good approximation of physical problems. And that's all well and good, but the problem is, and maybe I'll just anticipate, this is true if there's only applied tension and we're talking about an infinite body. If you apply just shear, the story changes, as we will see. It was mentioned in passing in the paper that shear deformation will also produce a small interpenetration zone, and as I just said, this is not the case. In 10, a paper by Ervigin in 65, again, it was stated, I return to this because this was the basic problem with interface fracture, with the stress oscillations and the interpenetration zone, and whether they're small or not. And in 10, it's found that for glass, between glass and steel, the interpenetration begins at a distance of order 10 to the minus 7A. So why am I keep harping on this? I'm harping on this because it was only done for tension. So then we have a paper coming out of Russia. It's still International Journal of Fracture, but Raphael Slaganek and I assume Malyshev were in Russia at the time. They again show that the stress oscillations are confined to a small distance from the crack tip, and the interpenetration zone is within a small distance of the crack tip. But again, shear deformation was neglected. It was pointed out in this paper that instead of an interpenetration zone, physically you're going to have a contact zone, and that sort of leads into Maria Komnenou, and we'll see that in a couple of slides. The authors also bring reference 12 to us, and I got a hold of reference 12 once again. I've seen it before. And in that reference, it's in Russian, but of course we can read the equations. And what Cherepanov does in 1962 is he finds the potential functions that from them you can find the stress and strain and displacement behavior, but he doesn't find the stresses or the displacements explicitly, and only finds for some special cases the potential functions. The main contribution of 11, in my opinion, is that they there define the interface energy release rates in terms of the stress intensity factors, and I'm giving it to you in current notation and not their notation, and not Rice's notation. The I, and you'll notice the G, I know some of my students are watching and they probably scratch their heads and are afraid to ask me, why do I use this silly looking G, the script G, instead of everybody else uses just a regular print G? Because I go back to Irwin, and Irwin used that script G in his papers in 57 and 58, and so I like it, and I use that script G. And this is the interface energy release rate, and it's equal to this to constants, mechanical properties, the oscillating parameter, and the sum of the squares of the stress intensity factors. So this is a very important contribution. So it would appear that as a result of the oscillatory stresses, even though they kept saying it's only in a small neighborhood, it must have bothered a lot of people because they lost complete interest in the subject. You don't hear anything about interface cracks. 1965, basically from 1965 to 1977, we don't hear about interface cracks. There is exception to that. In 71, there were 2 papers by Erdogan and Gupta. But what they were doing was they were looking at multi-layered composites, and they only took an interface crack as a limiting case. And then I believe the first paper in which somebody did something with finite elements and interface cracks was from 1976. But really, there's a barren period between 65 and 77 when it comes to interface cracks. And Maria Komnenou comes forward and says, let's solve the real problem. The real problem is when we have contact zones at the end of the crack tip. And so what she does is she looks at the problem of tension, she looks at the problem of pure shear, and then she looks at a combined problem of tension, compression, and shear, and she finds these contact zones. And she also finds the behavior of the stress field, which I'm not going to go into. So in 16, she shows that when you have far field tension, the contact zone, the length of the contact zone is between 10 to the minus 7th A, where A is half the crack length, and 10 to the minus 4th A, which is really small. So we see with really a physical method of carrying out this problem that we do indeed have very small contact zones. The contact zone was smaller than the interpenetration zone calculated from the approach of Rice up until then. But then in 17 for pure shear, and this is where everybody got it wrong between 63 and 65 or 62 and 65. There are two sides to the crack. So one side has a contact zone, which is even smaller than the pure tension zone. The other side has an interpenetration zone, which is 2A over 3. It's 2/3 half the crack, or it's 1/3 the crack length at the other tip. And the side at which you have the larger zone depends on the material properties and the direction of the shear stress. But one of them is going to have a large one. And so somebody put on their unmuted their microphone because I hear myself. So the small contact zone is larger than the interpenetration zone, which doesn't really matter. It's small. So the problem really is, and Maria puts it in perspective, the problem is when you have large shear. And the thing that you have to do is for your particular problem, you have to examine the zone. So we could say, let's just use the Maria Komnenou method for other geometries, but it's not practical. It's very complex. It's you have to solve integral equations and so on. And I don't think that that's the way that the engineers want to go. So Jim Rice comes into the picture at that point, and then he writes this seminal paper from 1988, which is not that many pages, but is just packed full with information when you go through it. And so what I'm going to do in the next slides is I'm going to talk about the paper, which gives us guidance of how to solve the problem, given the fact that we have an interpenetration zone and oscillatory stresses. So in the paper, I'm going to summarize what was done in the paper. Mushkulishvili was used to find the potential functions for the interface crack, and the tractions along the interface were found sigma 2,2 plus I sigma 2,1 at theta is equal to 0 along the interface. as kr to the I epsilon. And so we see the oscillatory singularity divided by the square root singularity. And k is equal to k1 plus ik2. And along the crack faces, he finds the jump. This is the jump in the displacement along the crack faces. And from this expression, we can find a size of the interpenetration zone. So the validity of the first term of the asymptotic expansion was examined in terms of the size of the region of crack face interpenetration. So if we consider this problem and we write the applied stress in terms of a size and a phase angle, psi, and we set delta U2 from the previous slide equal to 0, we can find the length of the contact zone, an approximation of the contact zone. And since, and we haven't really looked at it particularly, but we will, since epsilon is a lot less than 1, if I choose epsilon greater than 0, if psi is between minus pi over 4, psi is a loading parameter. So if it's between minus pi over 4 and pi over 2, then RC over 2A is very small. And so the interpenetration zone is small. And so now we can use this approach to discuss interface fracture mechanics. All we have to do is find the size of the interpenetration zone. And if it's small, we're in good shape. So if we look at epsilon, and let's examine epsilon. If we take material, this is what he does. He takes material 1 to be cork so that nu 1 is approximately equal to 0. And material 2 is much stiffer than material 1. So mu 1 over mu 2 is approximately 0. You can then show a bound for epsilon as 0.175, which is small. It's not very small. It's small. And if you switch the materials, if you put material 2 on the top and material 1 on the bottom, all that does is change the sign of epsilon. And so epsilon will be bounded by 0.175. And if we look in particular, and he gives about 8 or 10 examples, silicon oxide and alumina, epsilon is 0.075, and silicon and copper, it's very small. So it's small. It's small, but you still need it. Okay, now I see I'm sort of starting to run out of time. So maybe I'm going to skip this slide and go on and mention something about the units. The units of the stress intensity factor, not only are they complex, but they're complicated. Megapascal square root meter to the minus I epsilon. Very strange, but if you change the units, you change the ratio of K2 to K1. If you change the units for a crack in a homogeneous body, you don't change the ratio. So this is a problem, and thus the opening and sliding modes are inherently coupled. So one thing to do is to normalize the units, and this, in that paper, the normalized units were written with the Roman numeral 1 and Roman numeral 2. And I prefer to write it with the Arabic 1 and Arabic 2 because I like to save the Roman numerals for homogeneous material so that we don't have confusion. Anyway, the units, though, become megapascal square root meter, which is exactly what we have for homogeneous bodies. And L hat is an arbitrary length scale at this point. And in the paper, you were advised to take it as a constant and not a function of the crack length. And I understand that very well, but you have to make the mistake of taking it as the crack length, and then you see why that statement is there. There are all kinds of gems in the paper. You can read it again and again and find one gem after another. And my group used L hat to correlate failure data with a failure criterion. So the in-plane stress field was given, and for alpha beta, I think I want to just go ahead because I think I'm only supposed to speak until another 2 or 3 minutes. So I'm going to skip all these nice things that were in there and maybe say something about, you can have a phase angle of the stress intensity factors, which is the arctan of this normalized K2 to K1, K2 hat to K1 hat. And the effect of changing L hat is to translate psi. So psi A is equal to psi B, and it's related to the log of the ratio of LA to LB. So this gives us a way of translating a psi axis. Again, it would have been nice to talk about this, but I'm going to skip it. So it's proposed in paper 21, which was written by Rice, Swo, and Wang, that you can have a failure criterion such that GC, the critical value of G, is related to a function of psi hat. And there wasn't any experimental data, but this led my group to use this in a failure criteria. So if you want to get a failure criteria, you carry out fracture tests, you obtain the critical load and the critical crack length, you calculate the stress intensity factors, and then you can calculate the energy release rate for each one of your experiments. You have to choose L hat, and then you have a psi hat one, which is related to L hat. And then you plot your data. You calculated your data from this using your crack length and P. And then we came up with a criterion, but as you can see, the data and the criterion don't fit well. And this G1C bar, this average value, comes from the data. It's the minimum value that's here. So this doesn't fit well. Now, how do you get it to fit well? You change L hat, and in changing L hat, you translate this axis. So here we go again. We are now using L2, and the criterion fits very nicely. You can use L hat as a fitting criteria. We tried to associate L hat with the fiber size. We tried to with the plastic zone size of the epoxy. We never were able to do it physically. We just used it as a fitting parameter. And so this is our failure curve. Above is failure, below is safe. In other words, if you have a structure that has this interface, and of course you had to manufacture the interface in the same way, and it has this interface, you calculate psi hat for this L hat, you know where you are along here, you look up, you calculate G, and if you're below, your structure shouldn't fail, and if you're above, your structure may fail, your structure will fail, is predicted to fail. Of course, we have data below, we have scatter, so we use probabilistic methods. That's for another talk. So that ends everything. And I ask if you have any questions, and the paper in which I wrote the first half on linear elastic and Alexander wrote the second half can be found in Structural Integrity in Life. And a book 2 years ago, a short book came out of this, the work that my group has done. And of course, today, as Jim said, he works on crevasses. I don't know if that's how you pronounce it. A crevasses. And if you look up in the thesaurus, it's a fissure, a chasm, a cleft, a crack, an abyss, a gorge, a split, a rift, or a ravine. And there is Jim out on the crevasses. And there is Jim. Okay, so if there are any questions, I'd be happy to take them. I don't know if we have time for questions.
Maybe one short question, if Francesco allowed. Anybody?
So maybe I'll just say one last word. What I tried to do was to present the contribution that Jim made to interface fracture mechanics, which without him, we would be nowhere today. I mean, maybe somebody in the year 2000 or 2010 would have come back and fixed us up, but we were lost. After 1965, we were lost. In the 1988 paper, you just read, every sentence is chock full of information. You just have to read it sentence by sentence and take everything out of that paper. And that's what I tried to do in the majority of the talk. And that paper certainly influenced, I think I started in 1990, I started working on interface fracture. And I was on, I think it was that year, I was on sabbatical at Wright-Patterson Air Force Base. And I was looking at a weight function for interface fracture, looking at Jim Rice's paper, seminal paper on weight. He took Buckner and he made it usable. So I took that Jim Rice paper on weight functions and did the same thing for interface fracture. That was in 1990. And then we used it in analyzing tests, but I'm talking too much, so I'm stopping and you can get me off, get me off the platform. Yes, yes.
This is the real G.
Yes,
Can you hear me now?
yes, I can see you and I can hear you. And that's the real G. Well,
I prefer this one.
okay, but I can't,
It's more complicated, you know.
I can't seem to get it in the letters that I can print in either in LaTeX or in Word. But thank you very much. I tried that. That's the best I could do. Thank you.
Sure. Perfect lecture.
Okay.
Thanks.
Thank you, Leslie.
Yeah, thank you from me too. It just brings back memories of half my lifetime. I've been puzzling about that problem.
It was an excellent paper, really.
Well,
Yeah.
you've written an excellent summary.
Thank you.
Yeah.
Okay. Now, let me remind Jim about 2/3 of his working life, because I will go even further back into the past. And let me put my presentation on the screen. No, I didn't. I'm here. Really? Okay, let's see what's going on. I'm trying to share my screen, but it really doesn't work. So
Did you hit
if I
present? Did you hit present now?
I did, but nothing happens. So what should I do, Francesco? You hear me? You can hear me. Do you have it? Yes, please. Yes, please. Please do. Aha. Dobro. Yes, yes. Okay. Okay, let me try again. Okay, I think I fixed it. Let me try again. Let me try again. Can you see it now? Yes. Okay, good. So let me start. My topic is J integral, and I will talk about its role in fracture mechanics. Of course, just to remind you why are we here today, this is a very nice photo from 2 years ago. I think Jim remembers it. And now let me say a few words about J integral as the conservation law. This is the approach that we followed here in Serbia, especially thanks to my professor Jovo Jaric. So a couple of equations from theory of elasticity, nonlinear theory, relation between strains and displacements, then constitutive relation, and finally equilibrium equation. And then for the strain energy density, for the W, we can analyze its total derivative by using its partial derivative, and then, of course, the rules that applies in mathematical terms. And then again, we use some special quantities like Kronecker delta and Einstein convention for summing via indices, so that we get in somewhat different form actually 3 integrals, or better to say 2 integrals if we decide to analyze 2 dimensions. So this k here is either x is 1 or 2, or as better known for us, x and y. And of course, I think you can notice that this already looks like famous Rice-J integral. And then again, just let us notice why is this so important and why is this the conservation law. Because if we apply it to the closed path, as written here, then for the homogeneous material, at least in the direction of x is 1, this integral will become 0 if it does not contain a crack. So this is more generalized way of approaching to Rice-J integral. But now a couple of other notes in that respect. If we take into account this another tensor equation and get another form of this integral, we will finally get to this form. And then by applying divergence theorem, we can once again state that for the closed loop, this integral is 0. And that maybe should be more better explained by using this schematic presentation of a closed loop around the crack tip. So if this is the crack, and we start, let's say, from this point, we can go this way all over around. This is C1, then C plus, then C2, and then C minus. Now, since along these 2 parts of the path, integral is 0, then we come to the conclusion that this quantity, which we now call J integral, is path independent, and also we should emphasize that this is valid for 2-dimensional plane problem, homogeneous material, at least in x direction, and without thermal body and internal forces. So that is fundamental approach. And now we can say a few words about practical aspects of the problem. It was shown practically at the same time that J integral is valid for Hutchinson, Rosengren, Rice stress strain fields. You can see them here. That means for nonlinear material behavior around the crack tip. And then again, it was also shown in original Rice's paper that J integral is actually the energy release rate. I could have written here that this is equal to the G, whatever we write it, in whatever way we write it. I like also this Ruzic's way. And that actually enabled the experimental evaluation. There is of J integral. There is a bit of complicated sketch here, but basically that was how it was first done with multi-specimen method, and then later on it was a single specimen method. And then again, not very long after 1968, we were able to calculate, to numerically calculate the J integral, of course, by using finite element methods, and also by applying these fields, higher fields. Analytical calculation was introduced, and that is often referred to as EPRI method. So there is a sound physical meaning, and there are all these practical consequences that allowed us to experimentally measure the integral, then to numerically calculate it, and then also to calculate it analytically. So we could use it as a fracture mechanics parameter, as a valid fracture mechanics parameter, as the parameter with completely sound physical basis. And now I will focus on the problem that is also presented in the paper, which is online published just yesterday, a joint paper by Leslie and myself, and it is on the interfaces. And what I focused on is actually problem of multi-material body that is in in our case, welded joint. So here we have weld metal with the crack at the center, then two different regions that we call fine grain heat affected zone and coarse grain heat affected zone, and then finally base metal. And in between all these four zones, there are three interfaces. You can see them here, they are denoted with L1, 2, 3, and of course on the symmetric side 4, 5, and 6. Now, knowing that original definition of J integral would not be path independent in this case, its material is heterogeneous in the direction x2. You can see that it's heterogeneous in this direction. So, and knowing this broader approach of J integral as a conservation law, we were able to make a modified formulation by introducing line integrals, closed lines over these interfaces. So here are the line integrals which are 0 because they contain no crack, but in combination of these paths denoted by gamma 1, which is this one, inside weld metal, then gamma 2, which is inside the heat affected zone, one of them, and gamma 3, the other, and gamma 4, which is in base metal, with already mentioned L1, 2, 3 paths around interfaces. We come at the end to the, we get at the end the expression which is relatively simple to evaluate numerically. And that was what we really did back in 90s. You can see here kind of a tensile panel. It is under tension. Crack is somewhere here. In this region, there is once upon a time, specially designed a mesh with singular elements. And you can see also interfaces enlarged here and not emphasized here, but I can show where they are in this not so detailed figure, so that you have the idea this is the base metal and then heat affected zones and then the weld metal. So there are now a few integrals that were calculated so that we can explore this path independency issue. Theoretically, we established that if we have an integral which would go like from here to through the weld metal and then through the heat affected zone, in that case we should add one line integral here so that we get path independency back. And in the same way, as we go further through other two regions with different material properties, we should add line integrals as we cross the interfaces. So this is why we have expressions like this. Now, this table has a lot of information, but I'll focus your attention just to those, let's say, the last row. So the values of J integral with the highest load that we applied. Load is irrelevant actually for this analysis. So we have these three integrals which are crossing the interfaces, and we have these three line integrals which should combine with J1, 2, 3, and then regain path independency, as we will see in the next slide. But we also have here J average, and J average is made as an average value of 6 inner paths in 3 layers of elements that lay inside the weld metal, so in the homogeneous material, so it should be path independent. Now these 3 layers are shown here. This is the mesh I mentioned with singular elements, which was blanked in the previous slide. So 8, 9, 12, 15, 18 is the first ring of elements, then 7, 10, 13, 16, 19, and then 6, 11, 14, 17, 20. Each of them have 2 by 2 Gauss integration points, so this is why each of them have 2 paths around the crack tip. And just to mention, these singular elements are something like this. Yes. Yes. Okay. But okay, let me see what's going on. Stop sharing. Okay, let's say stop sharing. Let's try again. Present. Browser. Is it back? We have it, great. So I think Jim will recognize this sketch. It is from his paper with Tracy, and it's almost 50 years old. Now, a bit of more analysis on this topic. You can see from table shown here that once we calculate these modified J integrals, as explained, we get very good results in sense of path independency, because you can see these values at the bottom. They are really with very small error, something like less than 1%. So that is within the numerical error. And also they are close enough to the average value, which is not exact, because of course the most of numerical error is focused around the crack tip itself. And just to go back for a second to show you that differences that we had for those 3 integrals that would cross the interface, as you can see, is almost 10%, something like 9%, as you can see from these 2 values. So that was the story about path independency, and that was my part of the paper with Leslie, but I still have one topic to share with you, and that is also kind of introduction for the next speaker, for Blagoj Petrovski. And it is still, of course, about J integral. It is about direct measurement of J integral. It is something introduced by Dave Reed 40 years ago, approximately. Also, it is for tensile panel and for elasto-ideal plastic material. So if we measure strains along the outer contours, as shown here, and also if we measure crack mouth opening displacement, it was shown by simple evaluation of all components of J integral that we can actually measure J integral. Better to say, we are calculating it by using measured strains. So those measured strains are something like this. You can see them here on the On the notch side, so this is distribution along this side, and you can see them here along the cracked side as real measurement. Now, elasto-ideal plastic material, it is shown here. It is simple to present it and use in both measurement and calculation. So this technique, which is rather simple, has been used successfully. And then after tensile panels, we try to use it in some different applications. Most notably, it was the pressure vessel, and Blagoy will speak in more details about it. But also what we did was to modify slightly original expressions by introducing bilinear law, so materials which are not necessarily ideal plastic materials, but they strengthen as it is more realistic for steel, all kind of steels. And you can see here instrumentation, strain gauges, it is all the same story. And also for the pressure vessel, we need to take into account biaxial stress state as indicated here at the bottom of the page. Anyhow, from engineering point of view, difference is not important. At the end of the day, it's just 2%, as you can see here. So also for not very large plastic deformation, this part is, this modification is not very important. So we can still use original expressions with enough accuracy. And that's what has been done, and that's what has been applied in many cases, including pressure vessels, large pressure vessels for testing of real structures. And so by doing so, we actually are applying J integral as crack driving force and JR curve at the same time, and I'll try to explain it in more details now. So classical approach is that we calculate crack driving forces, that is J integral, with fixed crack length and by varying the loading, and then we get a set of curves as shown here. At the same time, we are using some kind of specimens like 3-point bending or maybe tensile specimens to get the JR curves, and then we compare them, and in these critical points, we get a critical value of J integral. And that is a classical approach in which we have crack driving forces versus JR curves. But then again, if we apply direct measurement of J integral on a real structure, like a pressure vessel, we are actually getting a point which is, in my own interpretation, neither crack driving force nor JR curve. I mean, one point can be the curve, but anyhow, all these points will not form JR curve. But it is simply a way to directly obtain the critical value. Since we are applying J integral on a real structure, then once it bursts or leak, we will have our critical value. Anyhow, if we want to get, if we would like to get JR curves by numerical calculations, then we might use micromechanical modeling. And this is yet another point in which I would like to emphasize Jim's contribution, because he was also the first to introduce micromechanical modeling. This is ductile enlargement of voids in 3-axial stress fields, famous paper by him and Tracy back in 1969. So it seems that by the end of 60s, as I already said today, we already had all tools needed for complete understanding on fracture mechanics, and most of them were established by Jim Rice. And that would be all. I just wanted to share this reference with you. You can see it online, and I think it is a very well written paper, and it was really a pleasure to cooperate with Leslie on it. Thank you.
Thank you.
Jim, but I think Jim is talking, but his microphone is muted. Jim, unmute microphone.
Okay, let's try that. Okay, well, just thank you for that absolutely highly educational major summary. And thanks to Leslie too for a marvelous presentation. These take me back to years very much earlier, and I must say I learned a lot through both presentations. And partly I learned a lot because I'm at an age when one forgets a lot.
Thank you, Jim. So let me announce Blagoj Petrovsky. He is taking over.
Okay.
Just a moment, I have small technical trouble. Blagoj is right by my side, don't worry. Ne znam zašto. Just few seconds more.
A gde su vam maske? Sebi u Blagoju.
Au, kakav propust. Na drugu stranu. So, wait, show. Okay, good afternoon. I'm happy COVID-19 avoid me, so I have opportunity to do first time in my life online presentation, and I hope it will be the last one because I'm 76 years old, so it's time to stop presentations. I would like to show you just small part of huge experimental project done about 50 years ago. At that time, it was like a rule that welded joints have to be overmatched, and inspectors were allowing only overmatched weld methods. But in meantime, industries started to ask for thin plates with high strength, and good toughness. And steel makers, they succeed to make such steels with yield point about 1000 megapascals. But producers of welding consumables were not able to produce such material in order to get overmatched weldments. At that time, Japanese researchers started to introduce undermatching, and
after a couple of years, a lot of researchers all over the world started to do the same. And 93 or something like that, Professor Schwalbe and Mustafa Kocak organized a big conference about matching effect in Reinsdorf near Hamburg. So I was testing high strength, low alloy steel, Japanese steel, Sumiten ATP, with high yield point about 800 megapascals and ultimate strength 840 megapascals, and with nice Sharpie value about 140 joules. Weld metal, in Serbian, it was welded joint was made by submerged arc welding. Wire was used US ATB and flux MF38B. Properties were about 600 yield point and 770 megapascals ultimate strength, with range about 0.76, and Sharpie value was 83 joules. And I hope with such wire and such flux, it was possible to get higher strength and also better toughness, but that was done. Here is presented MTS machine, 1000 kilonewton capacity with mounted tensile panel, and this panel was highly instrumented with different instrumentation, including linear value transducer, a lot of strain gauges, ring gauge, and also some photoelastic coating to be able to monitor plastic deformation. Design of these tensile panels was related to capacity of tensile machine, and my plates were 16 millimeters thick, so I was not able to use wider plate than 75 millimeters. At that time was very modern to use wide plates, which was frequently used by Rudy Denis. But I cannot say that I have a wide plate, but it's a tensile panel. I used to research 3 different situations. One was base metal, another was welded joint with the crack positioned in the middle of welded joint, and third situation was panel with the crack positioned in heat affected zone. So here you can see 3 linear variable transducers, which are used to calculate overall strain. Gauge length is about 230 millimeters. So include welded joint and also a lot of base metal. Strain gauges are placed on front side, on notched side, on back side, so-called unnotched side, and also from side. For J integral, are used only strain gauges on front and back side, and strain gauges on the side were used just in order if some strain gauge failed during the test to compare and eventually to correct this value. The most important instrument here was specially designed CMOD ring gauge, which has gauge length about 0.4 millimeters. So this ring gauge was able to be put it exactly direct on the notch on the specimen. So notches were made by electrical discharge machine, and after that crack was sharpened by 3-point bending stick, and deep of the crack was monitored by unloading compliance. So after certain number of fatigue cycles, fatigue was stopped. Unloading compliance was taken by load, unload using load in elastic part, and we were able to get surface crack with deep about between 2.5 millimeters and 3 millimeters, and length of this surface crack was 16 millimeters. So this crack was called small surface crack. It was designed in order to get gross section yielding. To compare the properties of JR curves for base metal and weld metal, we used 3-point bending specimens, 15 times 15 millimeters, tested at room temperature, and we can see huge, big difference between J for base metal and for weld metal. Again, if welding procedure was better obeyed, maybe it was possible to get better J values and higher tensile strength of this material. Tensile panels without crack were tested in order to get behavior, to get properties. And base metal panel, after 10 millimeters of elongation, experiment was stopped because capacity of machine was exhausted. And in order to avoid the problems with the machine, specimen was unloaded, but welded panel fractured at about 12, 13 millimeters of elongation. So test was run with displacement control with about 0.5 millimeter per minute. Next test was testing of tensile properties on panels with small surface crack. Here we can see different behavior of welded joint and heat effect zone and base metal. Welded panel break after 3 millimeters of elongation, and with tensile properties lower than base metal. Base metal failed after 19 millimeters of elongation, and it was like heat effective zone. They show gross section yielding. So after starting plastic deformation near crack, plastic deformation was spread over the base metal, and we had the gross section yielding. A remote strain was calculating using measurements of strain gauges remote from crack. Normally, the last strain gauge in the row of strain gauges, and normally that's average strain on notched and unnotched side. For weld metal, we can see that a remote strain was elastic. So for all experiments, remote strain was constant, about 0.3%. For heat effective zone, it was after 4 millimeters, again with small remote strain, but after that, plastic strain started to spread into the base metal. There is here one part where base metal and heat effective zone behaved on the similar way, but heat effective zone after 11 millimeters of elongation failed. Base metal was able to sustain 19 millimeters of elongation, and remote strain was about 5%. Local strain is the strain measured on strain gauge which was placed on other side of the notch, and it shows locally behavior of the weld metal or heat effective zone. At the beginning, we have the same situation, elastic deformation. After that, we have raise on local strain, practically similar for all specimens. But after 2.5%, weld metal was specimen was breaking. Base metal shows constant value about 1.5% till 5 millimeters of elongation, and after that grow and ended about 8%. Because of strain gauges, it's normally capacity of strain gauges was 10%, but because of necking, many strain gauges failed earlier. So if we have such 8%, so that means strain gauge was properly placed and it was done good job. Heat effective zone, it's something between welded joint and base metal, and both specimens show gross section yield. If we compare local strain against a remote strain, that's interesting for heat-affected zone. We have at the beginning everything happen in weld metal. So during this situation, remote strain is constant till 4.5 millimeters. So that means remote base metal is elastically deformed. Local strain is growing, and at about 4.5 millimeters, we have a remote strain of about 0.4%, but local strain about 2.3%. After that, we have remote means plastic strain spread to base metal, and remote strain was growing similarly like local strain, but local strain is a little higher. It's interesting to see crack mouth open displacement, the total displacement. We can see increase of CMOD in weld metal. That shows of position of crack in weld metal. During the test, it was recorded load against CMOD. We have different points at which experiment was stopped. Unload, reload was done in order to get unloading compliance, to calculate crack length. With measured values from strain gauges and CMOD, it was possible to calculate J integral. So we have values to construct JR curve. Here are given the numbers of strain gauges, and in proper Excel table, when we have distance of strain gauges on front, on back, on side, and all these measured values, it's possible to get such strain distribution on back, on front, and so on. In this way, it's possible to do for 3 specimens together or for 1 specimen, but for many steps of loading. In such experiment, it was possible to calculate contribution from different constituents. From here given for heat-affected zone, total displacement was divided as displacement in weld metal, displacement in base metal, and CMOD. On unnotched side, we have displacement in weld metal and displacement in base metal and total displacement. JR curves, you can see here. That's weld metal is much lower than heat effect is on base metal. And at the end, one can see strain distribution using photoelastic cone. Thank you.
Okay, that was Blagoj Petrovsky and the direct measurement of J integral. And I believe we can have very short question, if any. And if not, I see Sinisha is ready. So Sinisha, please take over.
Yes, I'm ready. Just share the screen. So you can see my window now. Oh, my sound is off. No, it's not. So can you hear me now?
Yes.
Yes.
And you can see my slide.
Yes.
Okay, good. First, I'd like to remind you that during his career, Jim Rice has made many important contributions other than in field of fracture mechanics. One of those important areas is diffusion in solids, and Jim has done work on geomaterials as well as traditional mechanics of materials, specifically in the area of stress diffusion interaction and cavitation in solids. The work that I'm going to present today is a teamwork. Rui Pan and Dusan Sekulic are responsible for experimental results. Experiments were done at University of at Harbin Institute of Technology. Sasha Kovacevic and I are responsible for theory and computations. Well, that's not exactly true. Sasha is responsible for computations. He has done the hard work. Some time ago, about 2 years ago, the experimental part of this team has presented us with a most interesting puzzle. It's diffusion bonding of ceramics, and in this case specifically zirconium carbide. So you take two. I don't need to tell you why is that important. Ceramics have many high temperature applications, and they're difficult to produce in near net shape. So you need to bond them, and then in high temperature applications, the part is as good as its weakest part, and the bond, the connection between two subparts, is the critical, is the weak link usually. So if you bond two pieces with a thin titanium film, in between, and let's look at first at the right-hand side. You put light pressure on it, I think 20 megapascal. You heat it up to 1400 Celsius. You keep it for 1 hour, and if you have a thin film, 10 microns, everything is homogenized. Everything is one phase. And you can see here energy dispersive spectroscopy. Concentration of all components are pretty much uniform. But if you have thicker film, not only that you don't get homogeneous bond, that is without residual stresses and all the troubles at high temperatures that non-homogeneous bond can cause, but this bonded region expands slightly. You get complex microstructure, and the process stops. Rui has done this for several combinations of transition metal carbides and transition metal film, and the story is pretty much the same. So now, since we are all bored to death with pandemics and Zooms and different video conferences, and since it's a special occasion, James' birthday, I thought I might spice it up a little. So, here's today's presentation. if you were wondering what I was doing during the pandemic's lockdown, now you know I have been binging on old BBC crime series. So if you think this was a terrible idea, blame the BBC. So during the presentation, we will first narrow the field. Well, the questions are obvious: who, why, what, so we will first narrow the field. Then we will look at some details and some clues. Then we will check the usual suspects, and upon applying method of elimination, we will make an arrest. Well, once we press the charges, the trial will consist mostly of forensic evidence, and there will be a verdict. So first, let's narrow the field. Ripan has also done long duration experiments, and they pretty much exclude the role, well, of kinetics. So if you ask why thin film gives you homogeneous joint, why thick film doesn't, it has nothing to do with kinetics. It's thermodynamics. Second, what is the nature of the characteristic length, that critical film thickness beyond which we cannot get homogeneous bond? Well, it's not very difficult. Dimensional analysis gives us the ratio of interface energy density and bulk energy density. So clearly, interface energy density will have to do something with it. But which bulk density? Is it chemical or elastic compositional or both? And why does the process stop for a thick film? Because it starts doing something, but we'll see why it stops. Okay, so let's look first at phase diagrams of titanium carbon and zirconium carbon combination. Phase diagrams are very similar, as you can see here. Well, on the left, we have first alpha phase, which is hexagonal at low temperatures, then beta phase, this is body-centered cubic, well, at high temperatures, and then with increasing concentration of carbon, we have phase transformation into the gamma phase. Gamma phase is B1 phase. It's like natrium chloride, rock salt phase. This is the heating history, right? We first heat it up. So several things happen. First, during the heating stage, we have alpha to beta transformation in titanium, and we have thermal mismatch, and that will all gives us some pre-strain or residual stresses, well, in the film and in the blocks of ceramics. Well, we could roughly write a sequence of events, although sequence should not be taken literally. Well, they overlap. First, we have alpha beta transformation. Then carbon diffuses, well, into titanium, and then titanium crosses into the gamma phase. We have beta gamma transformation, and then we have binary diffusion, titanium and zirconium mix, and that's driven by entropy. That's fairly simple. So we can leave that out. That will happen anyway once you have phase transformation. But the critical part is this: well, carbon diffusion and beta to gamma transformation. So we will focus on that. So let's look at, well, our usual suspect. Why carbon diffusion happens and what drives it. So, well, this is the initial carbon concentration at the interface. This is the interface. First, we have a jump, right? This is beta titanium. This is zirconium carbide. So let's throw a little bit, well, of this carbon from the ceramics into titanium. What will be the change in total potential energy of the system? We know systems will spontaneously move to lower their energy. So what do we have? We have, well, chemical or stress-free energy in titanium and in zirconium, that's in blue. We have elasticity and load. We have that constant applied stress from sides, you remember, well, from this side. So there is a work potential, well, load potential. And the there are elastic compositional energies. We take compositional energies as eigenstrains using Vegard's law. And we have change in interface energy. Now, sometimes this change in interface energy may look, well, like an afterthought, but we will see that it is actually crucial. Now, if you do analysis in details, first of elasticity, using the Vegard's law coefficients, how much, well, eigenstrain you get, and the work, and how much one material expands, the other one shrinks, you concluded that this red part must be greater than 0. Then we look at chemical free energy, and we look at free energy curves, which we obtained using thermocalc software. And you also conclude that that must increase, which is not really surprising, given that both materials are initially near equilibrium, right, here and there. But the total energy must go down. Therefore, the change of interface energy must be negative. Not only it must be negative, but it must be negative enough to counteract, well, all these positive parts. Well, otherwise you won't get, well, any diffusion. There's nothing to drive it. So to conclude, once you eliminate the impossible, whatever remains, no matter how improbable, must be true. Well, interface energy must depend on, in some way, well, on concentration, but the only thing that is attached to the interface is this jump, right? These are values in the, well, in the bulk materials. Only this jump, C plus minus C minus, is attached to the interface. So if we do rough estimates, this is a very difficult problem to solve. It's non-linear because of the chemical energy. And you have moving boundaries. But if we do rough estimates, you throw a little bit, well, you make some approximations, we will get our critical film thickness, where beyond which you cannot get homogenization. The process stops at about 40 microns, and our experiments say between 10 and 50, so it's order of magnitude. That's good enough. We can make an arrest. It is interface energy dependence on the concentration jump at the interface that must be responsible. This is this gamma prime, and you here have all the other usual suspects would compete with it. Right, this change must be greater in magnitude than this denominator to get our process going. So, moving on to the trial phase, our main forensic expert will be the phase field model, computational phase field model. And for those who are not familiar with those models, I will just briefly describe them. We introduce diffuse interface interpretation. Phase field variables varies between 0 and 1 over some thickness h. And then our chemical free energy is a function of phase field and of concentration. Our elastic energy is function of strains, concentration, and phase field. And then we have two parts. This is a basic interface energy, gamma naught, when there is no jump. And there is a part dependent on the jump. And when you have diffuse interface, jump means gradient, that is integral, over the gradient. Those parameters, kappa phi and kappa c, together with energy barrier, delta F between two phases, are uniquely determined from our presumably physical properties, gamma naught and gamma 2, and computational interface thickness. So phase field model is well suited for quadratic dependence. We still don't know what we do for linear dependence. I will return to that issue later on. Elasticity contains eigenstrains based on composition in Wegener's law, and our governing equations give us second-order diffusion equation for phase field, which is not conserved, while concentration, which is conserved because of this term in the energy, will be fourth-order PDE. And of course, we have mechanical equilibrium. So when we solve 1D problem, here's first the case with a thin film, 10 microns titanium film, 1400 Celsius. This is the composition, experimental composition, everything more or less uniform. And these are the stages of our simulations. We start from a dashed line. Green is concentration, so we have this jump. And then this green dashed line moves into the pale green. And in the end, it's a solid dark green. Our phase starts with a dashed red, then pale red, and then solid red. So we have full transformation, everything is uniform. Now, if we try to do thick film, our experiments showed that our film actually thickens. Well, this dark region thickens, and we have this kind of carbon distribution here. Look at just the right-hand part. This corresponds to the green line. These are simulations. So we start from a phase which is at a dashed red line and concentration which is at dashed green line. And in the end, our phase moves into the carbide. We get transformation into beta phase of zirconium and mixing, of course, an experiment of zirconium and titanium. And our concentration stops at a distribution like this, and there's no more motion. This concentration is just not enough to tip titanium over into gamma phase. So these are direct simulation of experiments, and you see very good correspondence. But then we can, by trial and error, try to find out what is the critical thickness. So if you try 10.9, and 11 microns, 10.9 will homogenize fully, 11 will not. So we say our critical thickness of the film is 11 microns. Our sharp interface model, and just to remind you, it was very rough estimate, gave us about 40 microns. And our experiments tell us that it is between 10 and 15. So the verdict is guilty. Diffusion bonding of zirconium carbide with titanium interlayer is controlled by interfacial energy dependence on the carbon concentration jump. That is the main culprit. The characteristic length, of course, is ratio of interfacial energy density and volume energy density. We have all the proof that we could possibly get. Well, our model fits the experiments very well. Finally, I would spend less than a minute discussing how should this interface energy depend on the concentration jump. It seems to be a rather important topic, which, to my knowledge, has not been considered much in literature. I couldn't find any models for this and any physics experiments. So, let's look at first case. Think of an imaginary crystal, single crystal, and think of a plane through single crystal, and that's our imaginary interface with interface energy 0, right? Because it's a single crystal. Interface energy is Gibbsian excess quantity. But now let me pack one side of that plane with some solid, let's say carbon. Obviously, I have to get some interface energy, and because of symmetry, this has to be some well, even power, or well, even function. Simplest even function is square, right? So that's where this term comes from. So we see that in principle, interface, just this little thought experiment tells you that interface energy has to depend on the concentration jump somehow. Now, where could this symmetry breaking term, well, this linear term, which will shift the minimum of the excess energy to certain concentration jump. Well, where does that come from? Well, there is no a priori reason why it shouldn't be there, unless you have some symmetry to stop it, to get some intuitive feeling for that. Think of, well, of a coherent interface between two crystals, and think about what happens when you pack this well, this crystal with a smaller lattice constant with interstitials, which will spread its lattice and make it fit the lattice, well, closer fit lattice to this larger lattice spacing crystal. So again, there is very little work, and both theoretical and experimental on this topic. And this is where I would conclude. And I just have to say, happy birthday, Jim.
Thank you.
Questions?
So any questions? Well, if not, this talk actually concludes the first part of our conference, which was 100% dedicated to Jim's 80th birthday. And now we will have 2 or 3 remaining presentations, which are more our local stuff. First will be Aleksa Milovanovic, and he will talk about some additive manufactured material and testing in the scope of mechanical properties. So he is also here right by my side. Aleksa, please take the floor, or the screen, whatever.
Okay. Yes, hello. I'll share my screen in a minute. Entire screen.
Not entire.
There you go. Some window. Doesn't know a window. Okay. 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 Do you see the presentation? Yes. Yes. Okay. Do you hear me?
Yes.
Oh, there's book.
And okay, completely set.
Okay, do you hear me? Sorry.
Yes.
Okay. Okay. Do you see the presentation?
Yes.
Okay, I can start now. So the topic is about fracture resistance of dental polymers used in dental practice. So to introduce you, the topic will be about the materials which are used in digital dentistry. Polymer materials used for making dental models, surgical guides, and aligners and other applications. So what digital dentistry means is that by using 3D scanning and 3D printing all combined, you may have quicker treatment and maybe more precise finished implants and aligners and such. So on the pictures below, you see from the left surgical guide. Then next to it, you have a 3D printed aligner placed on a dental model. Next to it, the picture to the right, you see fabricated dental models for application of making crowns, what the dental technicians next do with it. First, you need to do 3D scanning, which is in the picture above. On the picture below, you see the modifications which technicians do with using the 3D scanned model and so on. So the topic will be the concerning aspects of mechanical properties of polymer materials used in dental practice nowadays, namely in 3D printing technology. Using 3D printing technology. So the best results concerning dimensional accuracy are best at VAT photopolymerization 3D printing technique. So by ASTM standard, it states that it is a additive manufacturing process in which liquid photopolymer placed in a vat is selectively cured by light activated polymerization. So in this type of process, photopolymer material is a thermoset polymer. So specific material maintains defined shape and cannot be melted and melted to liquid and be irradiated to a new shape again. So by making a model from a thermoset plastic, the process is irreversible. The most well-known term for photopolymerization technology is SLA, which is short for stereolithography. In that type of technology, you have light source, build platform, and resin tank as main components of one such 3D printer device. So in that process, you use a liquid photopolymer resin, which is placed in a tank, which has a transparent bottom. Below that, you have a UV laser, which shoots a laser beam toward the XY scanning mirrors, which directed to the transparent bottom, curing, photopolymerizing a liquid in that tank. So by lowering the platform into a vat, into that particular tank, you have enough place between a build platform and that transparent bottom, just one layer height, which then cures by using a UV laser, and the platform, when finished, goes up. Then the sweeper circulates the resin, and with layer by layer manner in such a way, you have a finished part in the end of the process. So the additive manufacturing includes, well, the first thing is 3D scanning. From 3D scanning, you may attain a CAD model. Then with the CAD model, with applied CAD model or point cloud directly from 3D scanners, you tessellate it, converting it to STL format, which is then used for slicing that model using dedicated slicer software for a particular 3D printer. As the end process of that slice software, you have a G-code used in manufacturing as a list of pathways of your machine, which it has to perform to finish a particular job. So then by using that G-code, you send it onto your printer to machine to finish the job, and afterwards, if you have if you need to you'll have post-processing of your model, if there are any supports or any such structures which have to be removed in order to have your model. Just to have in mind, process parameters such as layer height, infill density, and so on, influence on mechanical properties of your finished parts. So with including more and more of the parameters, you'll have better insight in the mechanical properties of your parts. So a little about polymer materials. concerning microstructure, it can be linear branched and cross-linked. Namely, the thermoset materials used in SLA technology are in microstructure cross-linked. So concerning thermoplastics, the other material, their process is reversible. So you can make a model, then liquefy it again, and so on. The thermoplastics are better for recycling your model, but thermoset materials are irreversible, so they cannot be formed again into another shape after the solidification. Then concerning polymer materials, the forces that law the microstructure of the material are van der Waals forces and covalent bonds. Covalent bonds are in the chain, and between particular polymer chains, you have secondary van der Waals forces, which affect properties of material, of course, in type, like in information or such. So if strain in plastics are large, yielding mechanisms occur, usually grazing and shear deformation. So like in metals, you have when in yielding you have dislocation of planes, but in polymers, if the temperature is low and enough high strain rates and triaxial tensile stresses suppress yielding and favor brittle fracture. So the polymers do not contain crystallographic planes, as mentioned, like in metals. They have two types of bonds, so covalent and secondary van der Waals. So the ultimate failure requires breaking of the covalent bond, but the secondary bonds, namely van der Waals forces, play a major role in the deformation mechanisms that eventually lead to fracture. So the factors that govern the ductility of such polymers are strain rate, temperature, and molecular structure. So usually, if yielding occurs, two governing mechanisms are shear yielding and grazing. In shear yielding, you'll have a slide with respect, slide of molecules with respect to one another when subjected to critical shear stress. And concerning grazing, you'll have formation of fibrils, and in between those fibrils, there will be microvoids, a void formation. On microscale, you see it on a tested material as a stress whitened region due to a low refractive index. So the gray zone is usually perpendicular to the maximum principal normal stress. On the picture to the right, you see the tensile specimen placed in grips in the ultimate tensile testing machine. So those lines are those stress whitened regions. So as I mentioned, you have fibrils, and in between those fibrils, you'll have voids. This is the on the picture to the right. You see how those fibrils and microvoids see how they look like on the SEM microscope. Then the crack tip behavior is governed by a Dugdale strip yield model. So if gray zone is small compared to the specimen dimensions, the length can be estimated according to a Dugdale strip yield model and the formula placed below. Now concerning the particular material, we were testing dental LT resin from the Formlabs manufacturer in Massachusetts, USA. The dental aligners are made using 3D printing technologies, are biocompatible, so they can be used in contact with the human tissue. The material is a class 2A long-term biocompatible resin material. It is a monomer based on acrylic esters. So a particular material has a high resistance to fracture and wear, which implies that it is a good solution for use for production of hard splints, retainers, and other directly printed long-term orthodontic appliances used in dental practice. Also, the material corresponds to some specific standards, including above-mentioned ISO standards. So concerning mechanical properties, the made aligners are designed to withstand loads creating during biting actions in a human jaw. in human mouth between upper and lower jaw. So hence good mechanical properties are required. We conducted 3 types of testings, namely tensile, compressive, and 3-point bending tests. On the picture to the far right, you see the prepared models after 3D printing. The tensile tests were performed according to ISO 527-2 standard for extrusion plastics with strain rate of 1 millimeter per minute with 5 samples per batch. We used a extensometer in one case, but because our specimens were too thin, and concerning the weight of the extensometer, we not only had actual loads, but the specimen started to create a crack in the place of the contact with extensometer knives. So only 1/5 of our specimens were successfully tested with extensometer, showing that there is a 29.7% mismatch in values for particularly elastic modulus obtained directly from the tensile testing machine and from the extensometer. On the picture to the right, you see in pale red, you see the curve attained from the extensometer, and the other curve is from the machine directly. Okay, so it was expected that there was a mismatch because the length between the grips of the tensile testing machine was 60 millimeters, while our targeted gauge length of the extensometer was only 25 millimeters. So the difference was really expected. So about tensile tests, monitored mechanical properties were elastic modulus, stress and strain at yield, and fracture stress and strain. You see the results, the curves on the stress strain diagram, and the results are placed in table with average values and standard deviations. There was a fine matching of all samples. They are all placed in the stress strain diagram. Concerning compression tests, we conducted them according to ISO 604 standard with strain rate of 2 millimeters per minute. The specimens are in cross-section 10 by 10 millimeters with height of 20 millimeters. This is how the testing, this is a fast rewind of our test. This is how the testing was performed. Okay, the final break. Second. Okay, so with this upper screw, we sort of had 2 plumb parallel surfaces for compression tests. The specimens were fairly smaller than the diameter of the screw head. So in compression tests, we targeted compressive stress and compressive strain at yield and fracture stress and strain. Also, you see the results from the stress strain diagram and the results with average and standard deviation values in table. Due to great repeatability of all 5 samples, also you have on the picture to the right offsetted curves for each conducted test to see the best representation of all 5 curves for all 5 materials. Concerning 3-point bending test, the testing was performed according to ISO 178 standard with 5 specimens per batch. Detected force in this type is relatively low compared to other tests. Our load cell has a capacity of 100 kilonewtons, so the first 200 newtons measured newtons will won't be representative because that load cell has a flaw in the first 500th segment, which is first 200 newtons. So for that, we used dynamometer of 5 kilonewton capacity for precise measurements. This is how the tests look like. I'll skip. Okay. So that's how the tests were performed. the monitored values for flexural strength and flexural and strain at fractional strength, and also flexural stress and strain at fracture. You see the curves on the right, and in the table, of course, each values for each specimen with average value and standard deviation. So the matching was also in 3-point bending tests good. So what we did, we wanted to see the aging effect on mechanical properties of particular materials. So after printing and curing, you'll have a curing of your 3D printed material from regular sources in nature, like sunlight and so on. So they'll affect on mechanical properties of your material. And concerning that the dental aligners may be used up to 3-5 days, we targeted 1, 3, 5, and 7 days to see the aging effect on mechanical properties of particular polymer. So all 3 types of testings were performed, namely tensile, compressive, and 3-point bending testing, which with 5 specimens per batch. Average results for tensile testing are shown in the table below. So the results show that aging affects an increase in tensile strength and fracture stress values, with decrease in overall strain values. Highest increase is both in tensile strength and fracture stress in between days 3 and 5, namely 12.8% and 9.6% respectively. The elastic modulus increases with older samples, namely the lowest average value was for the specimens from the day, which were only 1 day old, and the highest value for the specimens that were 7 days old. Then concerning compressive tests, show that until day 5, specimens show increase in compressive stress at yield and compressive strength, with decrease in overall strain. Highest increase in compressive stress at yield and compressive strength is between days 3 and 5, namely 15 and 11.7% respectively. In day 7, there was a decrease in compressive stress at yield and compressive strength, with increase in nominal yield strain. Just between days 5 and 7, we assume that after day 5, compressive properties of materials stabilize from the aging effect. And last, concerning 3-point bending, results show highest values for flexural strength and flexural stress at break for specimens from the day 7. Only mismatch was from the increased strength are specimens from the day 5. They have a decrease in strength and stress at break compared to specimens from day 3, namely 15 and 9.9% respectively. Lowest values for flexural strain, both at flexural strength and at break, are present in specimens from day 7. In overall strain, there is no clear difference between specimens in day 3 and 5, but in day 7 you have a clear difference. So to conclude, the impact of 3D printing technologies in dentistry is significant, with promising future development in using more plastic polymer materials in dental practice for surgical guides, aligners, and dental models and such. The mechanical behavior of 3D printed part affected with certain loading conditions is difficult to predict. Hence, you need to take as many parameters into account to have better insight into setting of the whole 3D printing procedure. So in our testing, overall results show that aging has significant effect on mechanical properties of tested materials. Older samples in most cases sustain higher stresses at the expense of overall straining. Just to note that the maximum forces transmitted in the human mouth are about 700 newtons in compressive loading case. So concerning our tests, we've seen that the results show at least one order of magnitude higher results than maximum recorded forces transmitted on human teeth. So concerning aging effects, all specimens show promising results, and that with aging, all the mentioned mechanical properties increase in value with a slight decrease in overall strain. Thank you for your attention. Just a second.
Thank you, Alexa. And Ružica has a question.
I will try. Do you hear me?
Hardly.
Okay, and now?
Okay, I hear you now.
Okay, good. Do you know which animal is the only one that cannot be kept in the zoos?
Homo sapiens.
Nope. Tasmanian devil.
Why?
Because the force on his teeth, he can chew through any steel, anything. So he cannot be kept in any cage.
Okay.
There is not so much. It's a cartoon on a Tasmanian devil, you know. Okay, I'm not trying to be scary. Perfect presentation.
Thank you, Ružica. And now, Alexander Grbović, another contribution from the Faculty of Mechanical Engineering here in Belgrade, will present his paper on fatigue crack growth. Alexander, please take over.
Good evening. So can you hear me?
Yes.
Okay, now I'm going to share my screen with you.
Yes, please.
Okay, is it visible?
Not yet, but going to be. Yes.
Okay, thank you. So this presentation, as you can see, is about fatigue of additively manufactured materials. You will see in next approximately 15 minutes, let's say, report about two projects that we are now, how to say, develop, and both projects are ongoing, which means that they are still not finished. And you will see through this presentation that we tried during this coronavirus situation, because many of these experimental activities have been postponed. We tried to play with the numerical methods and try to simulate some crack growth in some materials like plastics. So the purpose of this presentation is to demonstrate the use of numerical methods in simulating the crack growth. And the goal is to analyze the fatigue strength of these plastic components that you're going to see in this presentation. So properties of material here came from the ANSYS material database of additive manufacturing materials, while the Paris coefficients that you can see on the slide were taken from this paper. So two different projects here will be presented: development of the robot for the educational purposes and development of the unmanned aerial vehicle. And like I said, both projects are ongoing, and I hope that for next presentation, for next meeting in a couple of months, I'll be able to show you also numerical, experimental results. So this first robot project is a project that we developed and started together with one high school here in Belgrade. So idea was to help high school students to develop their skills in design, in programming, and also in 3D printing. So idea was to develop a robot that would be at the same time cheap and easy to manufacture. And the purpose of this robot is to help children with disabilities to learn words. So you can see here, this was the initial model of the robot designed in one CAD/CAM software. And you can see that it has a shape that is, let's say, adjusted to kids. It looks like a toy. And here you can see two holes. One hole is for smaller screen, which will be used to send some messages to kids. And then this bigger hole is for a bigger screen, which would be touch screen, so kids can can touch the screen and then select some images, and then they will hear the exact pronunciation of that word from the robot. So also here we have 2 holes for cameras. So we plan to develop some software which will recognize the face of the kid, and then to enhance this communication between the kids and the robot. So because it should be cheap, and we know that ABS filament is priced at least than 50 euros per kilogram, we decided to create the whole body of the robot using 3D printing. And the total mass of all equipment that will be here situated in the robot's head is around 300 grams. So this info is important for next slides, because this is the force that we're going to use in our simulation. So first, we helped kids in that high school to prepare the model for 3D printing. So we learned them. We to show them how to use all these technology. And you can see here in this video that they defined the method for printing this head. And also we discovered that one of the critical moments here will be when these separated parts should be joined together. So there is a kind of bridge that will be created here between them. And then the idea was to identify these critical steps in printing, like this one that you can see on the screen at the moment. This left-hand side and right-hand side are joining together. So the kids were learning about how to adjust the printer settings, how to identify critical steps in the printing, and how to find the optimal model for printing and optimal settings for 3D printing. So you can see in this slide that all these attempts were successful. So you can see here several failures, and in almost all the cases, the reason were these bridges. When the 3D printer was trying to connect 3 separated parts. Also here, the thickness of the robot's head was varied, and the motion of the printer's head was analyzed, and etc. So kids were trying to find the optimal model for their printing. And after many trials, they got to this. Successful. 1/2 of the robot's head. And during this development of this head, so I came to ideas that maybe it would be nice to try to simulate here the damage spread in this robot's head, because we saw on previous slide that not all parts of this head were printed effectively and precisely. So this is why I decided to create a simulation and try to identify will the cracks that might appear in these areas. You can see here now on the screen, to identify will these cracks will grow and in which direction, and what is the approximate number of cycles that will lead to final failure. I say cycles here, the purpose of this robot, because this was first prototype, was to, like I said, to help in high school to learn how to assemble, disassemble robot, how to assemble electronics and all other devices, cameras and so on. So this robot will be assembled and disassembled many times during and it will serve for practice. So this is why here I decided to create several models, finite element models. And as you can see here, I initiate the crack here first at this corner here. Load used here was 3 newtons. I said before that approximately these screens and electronics will be around 300 grams in total. So we apply that force here in this area where most of these electronics will be attached. And then we use Paris law coefficients from paper that I showed on the first slide. I said that we in the future, I hope very soon we're going to carry out the experiment and then to find the coefficients and to find the real properties of this material. But at this moment, we used these properties that we found in the literature. And we can see in this first video on the top the crack growth in this half of the robot's head, and we can see the failure. And we can also see that the mesh was adapted during the crack simulation growth. So we didn't use constant mesh. So this simulation was performed in ANSYS, and ANSYS uses technology which is called SMART, or SMART technology. This technology is based on remeshing, the area around the crack tip before every new step of crack propagation. In this new video, in the second video, you can see the change of the stress intensity, of the stress in a crack tip, and of course we use these values of the stress around the crack to calculate stress intensity factors. So this next slide shows that SF, so stress intensity factors are high. So initial crack values are around 500 megapascal millimeter root of millimeter, and we can see as crack grows that these coefficients are rising, but after some time, around let's say this is 11th step of the crack rock, they start to decrease, and immediately before final failure, these stress intensity factor around 500 megapascals, so very similar to initial crack. So number of cycles in this case was very low. You can see that crack length of crack, final crack, was around 5.25 millimeters, and number of cycles was only 14, which means that with this kind of plastic and with this thickness of a head, so these kids in high school, they can assemble or this robot maybe approximately 14 times. Again, numbers here used for properties of materials are not from the experiment, so we'll see maybe get better results after we examine that material. Okay, the second project, before I move to the second project, this is was the simulation where we use another position for crack. So we assume that crack will now grow from this corner, but very soon we realized that all stress intensity factors were negative, so crack will not go if some damage, here. Then the third position of the crack was at this corner here, and again we got immediately that all stress intensity factors are no. So again, crack will not grow from this position, so definitely crack possibility that crack will occur here, and then it will grow through material and then destroy this head is highly likely only from this position. Okay, second project was a little bit more serious, but okay, I will not say that previous project was not. So this is an unmanned aerial vehicle project in which we developed several components by using and manufactured several components by using additive manufacturing. So here you can see vertical tails for this vehicle, and both vertical tails here are made by AM. And also we use metallic parts to attach these tails to the main body of the vehicle. And then idea here was to analyze and to estimate the fatigue strength of this tail. Load in this case is air pressure. So air pressure was obtained, distribution of air pressure was obtained in the software for CFD analysis. And then we imported pressures from that CFD software, and then found that total deformation is relatively high of these tails. It's about 1.6 millimeters, as you can see here. And the question was, due to this very high deformation, we realized that this tail is very elastic. But the question was, is this part reliable from the point of view of fatigue life? So again, we use the same method as described before. Several locations here for crack initiation were considered, and then we define initial crack at this position here first. You can see it on this image. Okay, this is enlarged image, and then got under these conditions, under this law that you saw on the previous slide, we got these stress intensity factors. Obviously, they're very, very low. Values are very low. Then for next step of growth, we got 1.98 megapascal, to be square root of a millimeter to be the maximum stress intensity factor. And using Parry's law with previously defined coefficients, we calculated the total number of cycles to grow a crack until final failure, you can see here, is more than 10 million cycles, which is for our, I mean, for purpose of this vehicle is more than enough, which means that this material can be used. I mean, that was our conclusion, but again, we need to carry out experiment and verify these results. Also, we inserted the different positions around these areas with a high stress, but again here we got very low values, and most of the values of SIFs were negative, indicating that crack will not grow in this direction. So conclusions: numerical methods, very powerful tool for fatigue analysis of the damaged structures made by AM. We can use several possible crack locations and analyze and find the most probable direction of the crack growth in a structure. Of course, the influence of the filament type and filament orientation must be considered, but again, when we get results from experiment, we'll be able to simulate and also define the proper orientation of the filament. Finally, the main advantage of the medical methods, and let's not forget, thanks to great Professor James Rice and other great scientists in this area, now we have these powerful tools which we can use to calculate stress intensity factors, J integrals, and everything, and predict the crack growth and fatigue life, which was impossible like 20-25 years ago. So, not to mention that complex shapes can be analyzed quickly once the material properties are, and then we can be, let's say, with very high confidence, we can be sure that our calculations and our simulations and predictions will be reliable. Okay, thank you for your attention. I hope that I didn't pass more than 15 minutes. Thank you.
Exactly 15 minutes. Thank you, Alexander. Excellent presentation. Any questions? Yes, Leslie?
Yes, first of all, thank you for that very interesting presentation. I wondered if you considered, since this is additive manufactured parts, that there's a certain amount of anisotropy in the parts when you're carrying out your analyses.
Yeah. First of all, talking about this vertical tail, I mean horizontal tail, idea was to use composite materials for this, and we made couple of we made couple of prototypes with the composite material, but it takes a lot of time. So this is why we decided to use additive manufacturing. So first, I worked on a composite model of the tail, in which I took into the anisotropy and all these properties in different directions. For this model made by manufacturing, additive manufacturing, I still don't have. I just don't have these anisotropic properties, but yes, I can include them in the model. I can model this tail layer by layer, and then define for each layer, define orientation, let's say, of the filament or fibers. Also, if there is some matrix here, if we talk about composite materials, I can define the properties of the epoxy. In other words, I can model complete materials. It's possible.
Thank you. Thank you.
Yes, Sinisha, please.
My question is, what do you know about residual stresses in the part after additive manufacturing procedure? Do you have any idea what they should be? Are there any reasons that we should expect? Well, I'm not really familiar with that particular procedure that you use, but I know that in additive manufacturing of metals, the final stage of sintering, if temperature is not homogeneous, you can get significant distortion, and residual stresses. So do you know something about residual stresses in your parts?
No, at the moment, no. But I agree with you. So definitely this must be taken into account. Honestly, this area of additive manufacturing is for us very, how to say, fresh and new. I'm professor at the Department for Aeronautics, and in aeronautics we mostly use metals, especially aluminum alloys. But in the last 10, 20 years, all these unmanned vehicles, drones, and unmanned flying vehicles are becoming very popular in the last decades. So this is why we started to analyze this area. But at the moment we don't have that, and we use relatively cheap 3D printer. We don't have printers for metal at the moment, but I hope in the future when we make this, when we analyze them, that we can get more info about this.
Thank you.
Thank you, both of you. Any more questions? I don't see any other raised hand. So in the meantime, I have talked with the last presenter, and we decided that we should postpone his presentation for some other occasion, because we are just 1 minute before the scheduled time, and we don't want to keep you any more occupied with this conference. So I suggest that we now have some final comments. I will say that I'm very, very glad that we made this conference. I guess it was a success, and I'm really happy that Jim could join us. So there are some advantages of online conferences after all, because if it were in vivo, we would certainly not be all together. It is really distances are really too big. So maybe some final comments from Leslie or Francesco, Ružica. I see Ružica is unmuted.
Everybody
or
should
Jim.
Everybody should unmute.
Yes, you can unmute now.
Everybody.
And just let us close the conference. Leslie, please.
Well, I'm really happy that I was here, and I'm so happy to have seen old friends, and in particular, I think we're so honored. We want to honor you, Jim, but we're so honored that you came and listened, and we were able to present to you all the different talks that we had, and I think it was a very wonderful afternoon, and I'm very happy that I was able to participate. And I thank you, Alexander, for making this effort. You worked very hard on it, even though you make it look very easy. And Francesco, of course, is always standing in the background, holding us all up. He gets us through all the tough times with the software, and he knows everything what to do. So we have to thank him for helping us. So
indeed,
Jim, thank
indeed.
you. I'm really happy that you were here. I'm so glad I got to see you, and because as you said, Alexander, if we were far away, we wouldn't all come close like we have. But because we are all so far away, and we're all huddling down and waiting for this car to pass us by, that it's good that we got to see each other. So thank you, Alexander. Thank you, Jim, and thank you, Francesco, and thank you all of the people who attended.
Thank you, Leslie. Now I see two raised hands, Jim and Sinisha.
Jim, you have to unmute. You're muted.
Or
Jim?
maybe that was
No,
before.
Jim raised his hand. You're still muted, Jim. You have to raise the bottom little tab. There's a line.
How about
There
that?
you go. There you go.
Now we get it.
Yes.
Okay, great. So this has been just fantastic. Just such an array of works that span a vast amount of territory, and I'm very grateful that you included me. And please do the same next year too. if it's going to be this good. And
Definitely.
also, of course, because I know a large number of you just so well over the years. It's just a wonderful time to see your faces again and to hear a bit about what's going on.
Thank you, Jim. Sinisha?
Jim, I am so glad to see you after such a long time. And looking at your haircut, I have to say, well, I'm glad you decided to let your inner hippie out, finally. Peace, man.
No, you know, this is fear of spreading of the virus, and so
I know.
I don't want to get near the hairdresser. But now, if I finally go back to the person who cuts my hair, they're going to be insulted that I thought that they would spread virus to me. So I feel like I can't go back. I can't stop.
I know. That's very stressful nowadays.
Alexander Grbovic.
Yes, I'm here, listening.
You raised the hand.
No idea.
Yeah, to wave to you,
Okay, okay. Ružica then.
I didn't think I will live long enough so that you will have longer hair than I do. Okay, so check your email tonight. And thank you, Sasha, for making this event. Leslie for fantastic presentation, Sinisha too, and everybody else. And Jim, thank you for attending this, making us, you know, proud to be able to see you and talk to you and enjoy this conference together with you.
Okay, well, thank you for being there.
Thank you,
Shall we all
Ružica.
sing happy birthday or not?
Yes,
Happy
indeed.
birthday.
Birthday to
Okay.
you. Happy birthday to you.
Happy birthday,
dear
dear
Jim.
Happy
Happy birthday to you.
Thank you. I'm afraid I've had a dreadfully large number of birthdays, but what you do? Time just keeps marching on.
That's
Only the
the
first
way.
100 years is
To
difficult. Then you
celebrate
get
it with
used to
friends.
it. As I said, only the first 100 years is difficult. Then you get used to it.
So I would like to thank also to Francesco. Indeed, without his help, I certainly would not be able to make this. And also one decisive moment when we decided that I really decided to have this conference, because it was last minute organization, as always. That's my part of my personality. The decisive moment was when Leslie told me that she would prepare her lecture. So thank you, Leslie.
Yes, thank you. And Leslie, now that we're on it, please do send a copy of that. It seemed like a marvelous tour de force, but it went by faster than I could take notes.
I'll send that, and I'll also send the paper, because there are words in the paper that don't appear in the talk. I will send it. I don't have your email, so maybe Alexander will send me your email.
I will send it, sure.
But you promised to review my book, but I think that I will steal your presentation as the introductory chapter.
Okay, so once again, thank you, everybody, and the conference is closed.
Bye.
Okay. Good fortune to all. Bye-bye.
Bye.
Bye.
I was working on a Thai project, so I did.